least learn something how they get the multiply. So simple assumption, but you do apply a lot of logic in between, and that is how this derivation stretched. Basically, they were able to get that Boltzmann distribution from here. But I mean using Boltzmann distribution. Okay, so the number of particles in the frequency domain is equal to the so 8 pi c to the power of 4 nu to the power of 4, and then d nu will be minus c lambda square d lambda d nu. So it became, so the minus and minus becomes plus. So 8 pi over c square nu square d nu. That is the number of particles between a frequency of nu and nu plus d nu. Okay, now this is where the whole problem arose. Now, since this photon has got energy traveling at the velocity of speed, and that is the reason that this theory is fascinating, because, okay, why don't we attach an energy? They knew that each photon, this is where the idea of quantum mechanics came. Let's say we attach a energy related to Boltzmann's, so this is the H is the Boltzmann's constant. I'm sorry, Planck's constant. So let's say it attached. So what is the energy? So let's say erase this one. It's a very small number. In fact, it's nothing but the gas constant divided by the Avogadro number, in fact. But anyway, if I attach it, so what is the energy density in this? So let's call this energy, okay? E nu d nu. So 8 pi c square nu cube h is there d nu. Okay, if I integrate that from 0 to infinity, I have to get the energy. I will immediately find that this is going to blow up. So the high frequency, so that was called ultraviolet, because ultraviolet has a high frequency catastrophe. So let's remember this. So energy density, if the number of particles still, will remember that. Let me just erase this, or maybe I can go to, I don't know that I can change it to some other place. Don't think so. No, I don't think so. Okay, I'll just erase it. I thought I can add one more. No, I don't think so. Some other software allow me to go to the next page. No, it doesn't allow me. Okay, that's okay. I have remember this. So basically, the number of particles I have is 8 pi c cubed. This is the energy, I'm sorry. They're not energy, number of particles. D nu square. Okay, instead of h nu, if I use the average energy, per particle. So that is where the whole brilliance of Max Planck came up. What exactly what is the average? Okay, suppose they used initially Maxwell distribution, they didn't get a good results. So eventually they used what is called Boltzmann distribution. Basically probability distribution. So the probability of a single photon or n photon, or formulated n photon, so n photons in a mode. Okay, that is basically the energy is En. There are n more. What is exactly is that is equal to the probability of that is exponential of that En minus En divided by kT. K is the Boltzmann's constant. He related that divided by the sum of all energy so n 0 to infinity or 1 to infinity, doesn't matter. State 1, 2, 3 and so on. Suppose En is nh nu. So what is the average En energy of the n particles? It is nothing but sum of n 1 to or n 0 is nothing, 1 to infinity of n nh nu exponential minus En over kT. See, remember this. You need to have probability has to be 1 if I sum it. If I sum this whole thing, this cancels out, becomes 1. So it satisfies all the requirement that it has to sum to 1. What is the probability of all up to 0 to infinity particle existing? It's obviously very obvious. It becomes 1. So let's just do this summation. So basically, he used, remember, this has to be non-dimensional. So kT is an energy, K is the Boltzmann constant, and this is energy also, h nu is energy. So it's still, it is a non-dimensional, so it is legitimate to sum this. So this is the basically how you're doing this. So let's assume x to be exponential minus h nu over kT. Let's assume that. So what happens here? So what is average energy? Is nothing but nh nu. So here is basically n, isn't it? So it's basically x to the power of n, isn't it? Divided by sum of here whole thing x to the power of n, and 1 to infinity. Or 0 to infinity, doesn't matter, it's 1, doesn't matter. So I can take h nu out and 1 to infinity of n divided by hn. Okay, so what is this series comes out to be? H nu, so n is 1, so x plus x squared goes on to infinity. I'm sorry, should be 2x squared, 3x cubed, so on and so forth, and divided by 1 plus x squared, blah, blah, blah. So that is how it became. So now we knew that 1 over 1 minus x, if I expand this in Taylor series, you will find is 1 plus x squared. So this is nothing but 1 minus x. Similarly, 1 over 1 minus x squared becomes 1 plus 2x plus 3x and so on. So this h nu, so E average becomes h nu. This is 1 over 1 minus x squared, and this becomes 1 minus x. There's 1 minus x. Only thing is you need to take an x out. Remember, this was x, so I am taking x out. We 1, 2x squared, and so on and so forth. So h nu x. So this 1x gets cancelled. So it becomes h nu. What is x? Nothing but h nu divided by kT. or minus, it doesn't matter. So it's minus. So they were divided by 1 minus exponential minus h nu over kT. So what happened here? What is exactly average energy? So this can be converted. This is, you subtract this, multiply this. So it becomes, if I multiply both sides by exponentials, it becomes, so average energy is h nu 1 over exponential plus h nu over kT minus 1. Okay, so instead of individual h nu, let's put that in there in our equation. See what happens. So that is the stroke. That is how that won the Nobel Prize. So instead of h nu here, I'm going to put h pi. This is the energy density. Okay, h pi over c cube h nu. Sorry, h cube d nu divided by exponential plus h nu divided by kT minus 1. Okay, all right, so that's the, so once it was there at high frequency, this goes to infinity a lot faster than that. So you will get a limit. So that is the way that the stroke of genius was. You were able to integrate that and then find. So what exactly we are doing is we got the distribution. So our energy distribution, only energy at nu was 8 pi. So 8 pi h nu h nu cube. I'm sorry, I should be h cube. Let's see what do I got here. So h pi h cube divided by c cube exponential kT minus 1. So this is the distribution of energy, basically the thermal energy between nu and nu plus delta nu. Now, what we are looking at is what exactly is the flux. In other words, what is the energy per unit time? So kinetic energy gives me is basically the energy flux is energy multiplied by c over 4, where c is the velocity, which is the speed of light. So if I apply that here, so my flux density, I'm just going to call this E nu, black nu, I'm going to call that as a energy density, is equal to E, this is E here, 8 pi h nu cube c cube. I'm just going to like that. This is E c over 4. So this is 2 and c becomes c squared. So I get 2 pi over c squared nu cube divided by this is my density. Okay, now I can convert this, nu, remember, lambda nu is c. So nu is nothing but c over lambda. Okay, so nu cubed will be c cubed over lambda cubed. So c cubed is c cubed, I'm sorry. So 2 pi over c squared, nu cubed will be c cubed divided by lambda cubed divided by 1 minus 1 over exponential h nu over kT. Anyway, so ultimately what you can do is I'm going to call this lambda. Okay, so I'm going to call this h nu. So this basically this can be defined as radiation constant C1 divided by, you can bring the lambda out, so lambda to the power of 5 multiplied by exponential C2, another constant, divided by lambda t minus 1. You can find this C1 and C2 are two constants. You can define it like this. This is the basic energy density in lambda domain. It's a frequency domain, we just converted into lambda domain. So if I plot this for each temperature, so here this is going to give us watt per meter square. Let's call this in the micron, okay? So divided by per micron. So you will find that the curve is like that. So every temperature, this is T is constant. So this term here, exactly like there is a maximum here where lambda m, this is where lambda m is for this temperature. So lambda m T is what exactly is the constant? Some sort of a constant. I did find it for something like 2 point. Let me see. Let's see. Something. I think I have it in my notes here. That's okay. I don't remember now. It's okay. That's all right. It's all right. Some sort of constant C1. I given everything in my notes. Let me just look at my notes here. Okay, so in the notes. Okay, so let's see. That's not what I want. Yeah, save and leave it. Okay. All right. So this is the curve. Okay, so this is the curve. The C1 over lambda 5, the C1 is the first radiation constant. It is Wm square. So, and then C2 is the second radiation constant, meter Kelvin. Obviously, lambda T is meter Kelvin, so it's a radial less. So this is lambda 5 will be meter to the power of 5. So lambda to the power of m cube, because this is per unit the density. So that is the reason. This is only that it's not the flux. Okay, so it's just the radiation constant. If I take the derivative of this, you will find lambda t is equal to 2.898 10 to the power of minus 3 meter Kelvin. So this each temperature, for each temperature you will get a different curve. So that is this particular curve is plotted here. Basically, is a watt per meter square micron. That's what when you integrate it out. Okay, so lambda. This is the curve that you get. Okay, so this should have been meter cube. I think probably this is correct because meter cube is per meter. Okay, all right. Okay, so once you get this curve, what else can you do? So let's go back to my white paper. Say so basically I can get, once this becomes a constant, so given the temperature, you know exactly at what wavelength this particular distribution of energy the black body energy will be a maximum. So that this is the nothing but Wien's law. So we can derive this. Let's do that in a minute. So basically we can take this equation, take the derivative. Okay, let's do that. So you have E black body in lambda is C1 over lambda phi and e to the power of C2 over KT minus 1. Okay, so let's call C2 over KT as U. Okay, so I'm going to take the derivative. So basically I want to know, I'm sorry, this is not KT, this is lambda T. I'm sorry, it's a mistake, lambda T. So C2 divided by lambda, not KT. That was H nu over KT earlier, but we have converted everything into lambda now. You know, new space was converted to lambda space using new lambda is C. So that is how the C2 also constant came in. So U is similar, or so let's say, so what is D? EB over lambda over D lambda. So if I take the logarithm of the right hand side, it's easy to do that, but it doesn't matter. So log C1 will be, if you take the derivative, it will be 0. So this will be minus log lambda phi minus log of U minus 1. Because C2 over lambda is like a U. So this becomes, if I take the derivative, so 1 over A B lambda. So it becomes 5 1 over lambda minus 1 over U minus 1. Okay, so lambda is nothing but, what is lambda? Lambda is C2 over UT. So this is nothing but 5 over C2 over U and T minus 1 over U1. This has to go to 0. So this can be taken as as some sort of a, so it's basically you will have to solve. So everything can be taken into some sort of a constant. How did that do that? Sam C2 over T is lambda U. All right, but it has, this is nothing but transcendental equation, because I'm sorry, it should be UU. I made a mistake. So it'll be 5 over lambda. Look, I'm sorry. Let's do this. Let's see. Let me do that in a minute. Okay. I take the derivative in a special way. Okay, that's all right. So, yeah, if you take the derivative, it will be a transcendental equation, and that's basically what you get is 5 over U if you take the Laplace. Anyway, that's, yeah, I have it here, but okay. So basically what you get is C1, okay, 5 minus 5 over lambda. So yeah, so that's okay. So basically C2, anyway, it's basically what do you get is lambda T becomes some sort of a 2 point. It'll become all the function of C1 and C2. You can take the derivative. I don't have the working out. If you take this one, it'll be a lot easier. This should be e to the power of u. So let's do that again. Okay, EB lambda is log EB is equal to log C1 minus 5 log lambda minus log of e to the power of u minus 1. Okay, let's do that. So let's take this the derivative EB lambda with respect to lambda. That's what we do. Where exactly it's maximum. So this goes to 0. So it's minus 5 over lambda minus 1 minus EU minus 1. And you have to take the derivative of nothing but u. That's all. Because you are taking the d over, basically d over du, because u is nothing but lambda. So I'm just taking the d bu over du rather than. So 5 over lambda, I should have done the lambda should be equal to the kt. So I can convert this lambda 5 to u to the power of 5. So that is what I did not do that. It could be just lambda u, because 5 lambda u log u. See, because I can convert the lambda 5 to u to the power of 5. So it will be u to the power of 5 c1 some constant divided by e to the power of u minus 1. So if I take the derivative, it will be like 5 over u. So it will be, I'm sorry. So 5, so if you take the derivative, it will be log 5 over u minus, this will be, it will be 1 over u minus 1 is 0. So it's nothing but, so 5 u minus 1 minus u is 0. So this has to be solved in a transcendental way. So u becomes something like 2.8 or something like that. So you can substitute that and then find out exactly lambda t. So u is constant. So lambda t is a constant. And then that constant can be learned from this constant. So you can find out what is lambda t. Based on that only, we are calculating the lambda where it gets maximum. So that is how all this maximum were determined using that. It's the lambda t is nothing but 2.898 10 to the power of minus 3. So you can, this will become combination of all these constants. Okay, all right. Now there is another trick that we have to play. What exactly is the energy? Suppose I give you a band. So this is given. You know that the energy density is given in terms of C1 lambda to the power of 5 e to the power of C2, I'm sorry, plus C2 divided by lambda t minus 1. Okay, so let's say I want to get what is the ratio of the energy. In other words, what energy is suppose I want to know what is the percentage of energy in a bandwidth, let's say lambda 1 to lambda 2. So I need to integrate this from lambda 1 to lambda 2 d lambda. Now, but the percentage is the complete radiation is, you know, it's lambda t to the power of 4. So the percentage of energy in that band is EB lambda integral divided by lambda t to the power of 4, isn't it? So if I do that, let's say from lambda 1 to lambda 2, C1 lambda to the power of 5 e power c2 divided by lambda t minus 1 d lambda divided by 1 over sigma t to the power of 4. Okay, suppose I convert this lambda t is a constant u. In other words, change a variable. So I put lambda t here, and then I put bring in lambda t inside. So t to the power of 5. So what do I get? So I get 1 over c1 over sigma. When lambda 1 is lambda 1, lambda 2 is u becomes lambda 1, some sort of constant temperature, lambda 2t. C1 has been taken 1 over u to the power of 5 e to the power of, see, lambda t is u, so C2 over u minus 1 and du. So this, what is the percentage of lambda t? So it so happened as a function of lambda 1, lambda 2 t, remember our lambda is only from 0.3 to about 100 micron. And you know the thermal energy. Otherwise it doesn't exist after that. So this has been plotted. What is the percentage from lambda 1t to lambda 2t? So from 0 to lambda 1t, if it is plotted, then I can calculate that, because say let's say 0 to lambda 1t is some sort of a L1, and then 0 to lambda 2t is L2. So I can get this as nothing but L2 minus L1. So I can determine the percentage of energy in this band using this. Then I can multiply by lambda t to the power of 4. If I do that, I get the amount of the percentage of energy, black body radiation in a bandwidth. Okay, so let's do that. I have plotted that. Let's just say I have a table. So let me show that to you. Okay, before I go here, let's just show here. So basically, I have plotted this between, okay, so look at this here. So lambda t is given. This is all in mil, so this should be multiplied by, if it is micron, should be multiplied by another 10 power minus 3. That's okay. But anyway, this is the micron and this is the ratio. So up to about 2 lambda t, 2 micron, you know, the temperature of something, it is hardly anything. It's only about 0.06 percentage or 6%, let's say. So if it's beyond, you know, it's very, very small if it's 0.2. However, if it reaches about 3.4 is 0.36%. In other words, 36%. It's 3.4 in the sense, let's say a body is 1000. So what exactly is how much energy from 0 to 3.4 micron is given by about 36% of that energy is in that. Then how much is the total energy in the watt per meter square is, you have to multiply by sigma t to the power of 4. So it's make it easier. Look at this. By the time it reaches 100 micron for 1 degree Kelvin, it reaches almost 1. So there's not much energy left. In other words, if I look at this curve here, if I curve here 0.1 micron, if our temperature is 1 degree, the ratio will be only 36% will be there. So let's do a simple example. I have maybe about a minute. We can do that. Let's see. Okay, so let's just very simple example here before we close. Let's assume the lambda t is a maximum. So basically an example is determine a wavelength at which a monochromatic emissive power of a tungsten filament is about 1400 Kelvin is the maximum. At what wavelength it reaches a maximum? I mean, what is the maximum emissive power at the maximum wavelength? That's one part of the problem. What is the monochromatic emissive power at that wavelength? And what is the monochromatic emissive power at 5 micron? Let's just do the first two problems. So the maximum max is obtained by this, basically the relationship of Wien's displacement law. So if I supply the temperature 1400 here, I can get lambda max. So lambda max is divided by 1400, I get 2.0, so 2.07 micron, I get the maximum power. In fact, if I look at this, the curve here, I did 1400. I don't know whether I have the 1400. Yeah, I have approximately 1400 somewhere here. If I look at the maximum there, it reaches around 10 to the power of 4, something. So where exactly it reaches? If I drop down, yeah, it's about 1 point. I think exactly correct. It reaches about 1 point. I mean 2.22 micron approximately. So approximately reach a 2 micron. Let's say 2 micron is here. Yeah. If I go ahead, 1400 is around here. Okay, it reaches around 2 microns. So it's correct. So that problem shows that it's correct. And what exactly is the maximum value of that? Again, we saw that it's very small. The max is this much. So I can calculate EBT at that maximum point. I get about 12.87, 10 to the power of minus 6, t to the power of 5. I had to multiply and then take the ratio. I don't have that number here. That ratio is approximately about 0.25 multiplied by the maximum value that you get the total emissive power. But anyway, using that simple this table here, this of course it has to be done numerically. This was all numerically done, but once you create this the table, I can calculate what is the energy at each band. I can calculate it. So that may be useful. So anyway, we'll continue tomorrow, and then we will hopefully I will have enough material covered by the time you have the test tomorrow. Are there any questions from anybody? Any questions? No questions?
No, sir.
Okay, all right. Then have a nice day and good day.
Thank you, sir.
Thank you, sir.
Thank you, sir.